All right. In this lesson, we're going to talk about equilibrium and also what happens if we have an applied force that is not along the plane or perpendicular to it. I want to take us back, and I just want to review what equilibrium means. Equilibrium means that the sum of the forces equals zero. So if I add up all of my forces together, the sum is zero. Now, when an object is in equilibrium, it can be at rest, or it can be moving at a constant velocity. All right, and in velocity, I mean both magnitude and direction. So it can either be moving in one direction at a constant speed, or and that's exactly what I mean. If it's turning or doing anything else, then it's not in equilibrium. We've seen this diagram before, where we have an object on an inclined plane. It has a force of gravity that points in the downward direction. We have a normal force, which is perpendicular to the surface, and then we have the force of friction, which is parallel to the surface. And in this instance, there's no applied force to it. No force being applied by an outside object. In this case, it's all strictly by the inclined plane itself or by gravity. And so if this object were to be in equilibrium, we would actually have a perpendicular component of our F sub g, or our weight. So we'll call that F sub g perpendicular. And we would have a parallel component, right, which we will call F sub g parallel. And we know that in this instance, because the object is in equilibrium, we know that F sub g perpendicular has to equal our normal force, F sub n. We also know that F sub g parallel has to equal our force of friction. Now that can be kinetic or static, depending on whether the block is moving at a constant velocity or if it's at rest. So I don't want to stipulate that that's going to be static or kinetic. It can be either or. So in this case, I gave you the equation that F sub n also equals F sub g cosine theta. All right, because if that's theta right there, then this is theta, and F sub g perpendicular is our adjacent side, so it's cosine. And I've also given you this equation where F sub force of friction equals F sub g sine theta, because F sub g parallel is the opposite side, and that's our sine function. Now when we start applying forces that are not parallel or perpendicular to the surface, we actually have to modify these two equations because they don't turn out to be accurate. Whenever we have that situation, we need to start analyzing the forces themselves. And so I've redrawn a new scenario, and this is going to be part of what our homework is about. And if you see now, I have a block. It's in equilibrium, or I'm going to call it in equilibrium, so that means it's moving at a constant velocity, or it's staying stationary. And I can actually prove that with numbers. And remember, you can apply a force and still not have an object move. So if I look at this, I have the weight. The weight's always going to be there, and it's always pointing straight down. I have the normal force, which is because I'm sitting on a surface, and it always points perpendicular to the surface. I have the force of friction, which points parallel to the surface and opposite the direction that the tendency of the object wants to move. So the object is going to want to move this way if I pull on it in that direction. So my force of friction points to the left. My force applied points up and to the right. And now this force applied is actually going to affect our normal force that's on our object. And so that's going to change our friction. And so I'm going to use this to explain some of the things that you might see in a grocery store later on. And we'll look at that and see how that works. In this case, though, if I were to look at all of my vertical forces, so if I were to sum up all of my vertical forces, so the sum of, and we'll call that forces perpendicular to the surface, So the sum of all the forces perpendicular to the surface has to equal 0. Because my object isn't lifting off the table, or it's not falling through the table, so the sum of all the forces that are perpendicular to the surface has to equal 0. And then likewise, if this object is in equilibrium, which is not speeding up or slowing down, or it's not turning, then I know that the sum of all the forces parallel has to also equal 0. And that's by a definition of equilibrium, which is up here. The sum of the forces equals 0, and so forces. All right. This little zigzag line is a mathematical operator that just means the sum. It just means I add up all of my perpendicular forces together and I get 0. I add up all of my parallel forces and I get 0. So if I look at this, I want to look at, well, what are all of my perpendicular forces? I have my normal force is perpendicular and it points up, so I'm going to say that that's positive. All right, so I have a positive normal force. I also have a force of gravity that's perpendicular, and so that's going to be a negative force because it goes down. And I have this force applied. Now this force applied doesn't go strictly perpendicular. Instead, we actually have two components of it. We have our parallel component, which looks like that, and I'll call this force applied parallel. And then I also have my perpendicular component, which I'll call force applied perpendicular. Now in this case, force applied perpendicular is up, and so that means that I'm going to have an applied force perpendicular that's going to be positive. So up here I'm going to put force applied, and we'll call that perpendicular. So the perpendicular force applied, and if I look, then I have this force, my normal force, my force of gravity, and my applied force perpendicular. And then that's all of my vertical forces, and so I know that has to equal 0. All right, by the definition of equilibrium. If I were to look at my horizontal forces now, or my parallel forces, well, I have the force of friction which points to the left, and anything that goes to the left is negative. So negative the force of friction. And then I have this force applied parallel that points to the right, so it's positive. Force applied parallel. And I know that those have to equal 0. Okay, once I have this, then I can start looking at how these equations change. In this instance, the only perpendicular force I had were two of them. I had F sub g perpendicular and a normal force, and so I have F sub g perpendicular, which was negative, plus my normal force, which is positive because it goes in the positive direction, we'll say that is, and that equals 0. So in this case, the normal force equals F sub g perpendicular. If I look down here, well, now I have this force applied as perpendicular. So in this case, if I wanted to solve for normal force, I'm going to go ahead and move this down so that we can look at it down here, and I can do all of my math with it. So I have the normal force minus the force of g plus, or the force of gravity, plus the force applied in the perpendicular direction, and all those equal 0. And I want to solve for my normal force. To solve for my normal force, which I'm going to use to find my coefficient of friction, I have to start moving stuff over. So let's start with this force applied perpendicular. It's being added, so I'm going to subtract it to both sides. Perpendicular, and I get Fn minus, oh, I'm almost off the screen. Fn minus Fg equals a negative force applied perpendicular. Okay. I also know that I need to move this F sub g over, so I'm just going to add it over, and I get my normal force now is going to be Fg minus the force applied perpendicular. All right, and so now I have this relationship of normal force 2 to the fact that I am now applying a force. And this force could be applied up like that, in that direction, or it could also be pushed down on it. And we'll see that in the shopping cart incident or situation, how we can actually make it easier to push a shopping cart. Notice it's no longer FG, it's no longer just one simple equation. Now I have to actually look at what are my forces doing, and I can even have this block on an inclined plane and have another force applied, and then I have to do FG that's going to be perpendicular to the surface. I have to do the force applied that's perpendicular to the surface. So there's ways that I need to manipulate these forces in order to get them either perpendicular to the surface or parallel to the surface. So let's look at a situation. Let's look at the shopping cart situation. So I have a shopping cart, and actually I'm going to stop the video and put it on the next video.